Hello, in this video I'm going to go through a motion question. It's a fairly straightforward question, but I want to spend some time delving into these key ideas that we've been looking at. So particularly the conservation laws for energy and momentum and the idea of work done as energy transferred from one location to another. All right, first of all, let's see what the question's about. They've given us a diagram. So let's see what's in the text that isn't in the diagram. We've got a child of mass 32 kilograms, so that's new info, uses a slide starting from rest at P. The curved section of the slide PQ is 1/6 of a circle of radius 4 meters. Right, they've given us the 1/6 and they've given us the 4 meters. The child is traveling horizontally at point Q. The center of this circle is at point O, vertically above Q. Okay, that's fairly clear from the picture. Section QR is horizontal and of length 5 meters, which they've also put in the diagram. Right, so we've got a few new bits of information. Assume that air resistance may be ignored. Okay, yeah, we always do. And assume that the two sections of the slide, PQ and QR, are both smooth. Okay, find the kinetic energy of Simon when he reaches the point R, and hence find the speed at point R. Right, okay. Right, so this horizontal bit is actually very useful, saying that QR is horizontal, because we're going to be thinking of all of this in terms of work done and therefore energy transferred. So work done is where you've got a force acting through a distance, and whenever that happens, energy gets moved from one place to another. So going from P to Q, we've got a force due to gravity, which is acting through a distance, the vertical height of P above Q, and that is transferring energy from gravitational potential energy into kinetic energy. So that's what we're going to be doing from P to Q. Now from Q to R, the fact that QR is both smooth, so there's no friction there, so you've got no force doing any work from the frictional point of view, and horizontal, which means there's no gravitational work done either. So there's no work done at all between Q and R. So we're going to have no energy transfer between Q and R. So whatever the energy situation is at Q is going to be the same at R. So although they've asked us to find out these things at point R in the first two parts of the question, they could equally have said Q there, because there's nothing really happening between Q and R. So from a work done point of view, we could say, okay, the work done due to gravity is going to be the force. So that's the force due to gravity is the weight. So our weight times the distance it is moved through. Work done is force times distance. That's mgh. And that is our energy transferred into kinetic energy, half mv squared. So our kinetic energy is going to be mgh. So we need to work out what this h is. So if we put in that dotted line, we can see we've got a nice right angled triangle there. PO is also 4 meters because that's another radius of this circle. So we're splitting this height into 4 cos 60, which is 2 meters. So it must be another 2 meters at the bottom. So we've split OQ in half. So our H is 2 meters. Our M is 32. So our kinetic energy is going to be equal to 2 times 32 times G, 64 G joules. We can now solve that to get V. We're going to have a what are we going to have? We're going to have a 32, so we've got to divide by 32 multiplied by 2, so we're going to have 4g and square root it, so 2 root g meters per second. So that's a work done point of view. Something I'm going to come back to at the end here is you might just say, okay, well, this is conservation of energy. Let's do GPE to kinetic energy on here, do conservation of energy. We'll say mgh equals half mv squared. Okay, that's fine. That is sort of what we're doing here. I've written it in a work done point of view. But we will return at the end of the question to have a closer look at the extent to which conservation of energy is applicable. I mean, obviously it is going to be pretty applicable because it's given us the same answer, but there's some slight intricacies in this, just as there are in this this work done equation here. But I'll save that for the end because I don't want to get too distracted here from the main thrust of the question. So we've done the first two parts. Now in the last part of the question, they're saying that QR is rough. First part remains smooth, so our calculations for what's going on at Q haven't changed. We're still going to have that kinetic energy and we're going to have that velocity at Q. So that's fine. Find the coefficient of friction if Simon comes to rest at point R. Right, so from a conceptual point of view, yeah, let's actually do this twice. Let's do the conceptual approach and the sort of faceless Suvat approach. So work done is the energy transferred, which is also equal to the force times the distance. So our energy transfer is that all of our kinetic energy at Q is going into frictional losses by the time we got to R. So we've transferred 64 G worth of energy, and that is going to be our frictional force, which is mu R, which is then mu mg multiplied by D, which is 5. So we just have to simplify all of this, solve it for mu. So cancel the G's. We're gonna, that M is going to leave us with a 2 there, divide by the 5, and that leaves us with what mu is. So mu is 2/5. So that's our conceptual approach, just thinking of work done as energy transfer. If we were going to do this as the faceless, let's go to the formula booklet, pull out some Suvat. So we can do our conservation of energy version of Suvat, the V squared is U squared plus 2AS, and our Newton's second law. We got loads of vectors kicking around on here, so let's make sure we're getting the sign of everything correctly. So we're measuring S off to the right. I'm also going to put the acceleration off to the right, but the friction, our frictional force, is off to the left because it's acting against the motion. So this is going to give us the sign of all of these values that we're putting in here. So filling this in, we got 0 is equal to U squared is 4G. 2AS, we've got A and S as being positive, at least in my picture. A will end up being negative, but at the moment we've got it drawn that way. So we're going to have 10A. Going to our Newton's second law, we're going to have friction, which is negative, which is our mu R, so our mu mg minus mu mg is equal to ma. So A is minus mu g. We just need to shove that into our first equation. So we've got 4g minus 10 mu g. And then we're solving that for mu. And once again, we get mu is equal to 2/5. So pleasingly, we got the same result. It'd be worrying if we didn't. And it just goes to show how all these concepts are built into these equations. You know, these Suvat equations and Newton's laws haven't come about by chance. Yeah, it's all built in there. So it's nice to be able to talk through it through using the first method, making sure we understand all the concepts, and see how they fit in with this, this more sort of standard approach. Right, so let's come back to looking at these conservation laws then. So we essentially use conservation of energy in the first part of the question. We've taken our GPE and we've set it equal to the kinetic energy. But we haven't been able to use conservation of momentum. You know, if we think about what's happening in the momentum, you know, this kid has gone from having no momentum sitting at P to having momentum sitting at Q. So momentum has appeared in our system here. We've gone from none to some. So why has that happened? You know, why can't we use conservation of momentum in this particular case? So this comes back to our idea of a closed system. So remember, we don't really want external forces acting. So these are forces that have originated outside of the system that we're considering. So in this case, the weight, the force that is acting, that's doing the work, that weight is coming from the gravitational force of the Earth, which is not in our diagram, it's not in the system that we're considering. So just looking at the child going down the slide with the effect of gravity, it's not a closed system because we've got a force that's coming from an object that's outside of that system. So if we were going to use conservation of momentum, we'd have to include the Earth in the system, and then we would see, which is what Newton's third law is describing, that the change in momentum of the child is exactly the same as the change in momentum of the Earth. So they both have the same momentum, but we've got the momentum of the child, little m, little v, because he's only got a little mass, and he builds up to this velocity here of 2 root g meters per second. That is going to be the same as the mass of the Earth, which is a lot bigger. It's something like 6 times 10 to the 24 kilograms or something. I mean, you're adding 23 zeros here onto the mass of the object that we're considering. So it's got a hugely increased mass compared to the child. So it's going to have a correspondingly small increase in the velocity. The velocity of the Earth is barely going to change because it's got such a huge mass, and that means it doesn't need much velocity to get up to the same momentum as the child, but in the opposite direction. So they cancel out and still maintain 0 total momentum as we had before the child went down the slide. So that's why we can't use conservation momentum. So why were we okay to use conservation of energy here? We don't have a closed system. The Earth is moving, it's picking up a bit of velocity here. So why can we do this GPE to kinetic energy and say that all of our GPE has gone into the kinetic energy of the child? Why is that okay? Well, really this comes down to it falls within the limits of the approximations that we're willing to accept when we're doing these calculations. Now, we've already got approximations just rife all the way through this. MGH is an approximation, and that's even aside from when we put in a value for G. As soon as we do that, we've got an approximation. But even if you leave it as G, as we have done in our answers, you've still got an approximation because we're saying that it's a uniform gravitational field if we're writing out MGH, whereas actually it's a radial field. Similarly, we're going to have small changes in mass due to motion. We've got these tiny relativistic effects. So we've got approximations already built into all of this that we're quite happy to ignore because they are very, very small effects. And we do have another small effect if we look at the energy. So if we think of what's happening, coming back here, looking at these, we've got a half mv squared for the kinetic energy of the child, and then we've got a half in the capitals mv squared for the change in kinetic energy of the Earth. So we can ignore these halves, these don't really matter, because we want to see how this kinetic energy is divided up proportionally. And we know with the momentum, we've got the same amount of momentum on both sides. How does it divide up for the energy, the kinetic energy? So we know that this big M is essentially 10 to the 23 times bigger than the little m. So we've got a massive 10 to the 23, say, advantage on the right-hand side. But because the momentums have to be the same, we've got the inverse of that happening for the velocities. So this velocity here of the child is 10 to the 23 times bigger than the velocity for the Earth. And we're then squaring that. So when we cancel all of these things out, we can see that almost the entirety of the kinetic energy is being transferred to the child and not to the Earth, because we're squaring the velocity, not the mass. So the big advantage that the Earth has is the mass, the big advantage that the child has is the velocity, and that velocity is squared. So we're as good as saying that 100% of the energy transfer is going to the child. There's a tiny amount, but it's so tiny, the kinetic energy, if we were going to make a calculation for what's being transferred to the Earth, that we might as well ignore it. If we're willing to ignore it's not a radial, it's a radial field, and we're going to ignore that and say it's uniform. If we're willing to ignore variations in the value of G, well, we're going to be willing to ignore this. So conservation of energy is fine in this case, because we don't really have any losses outside of the system. Whereas for conservation momentum, we do, because that momentum split is 50-50 between the child and the Earth. So it's worth having an understanding of when these things work and when these things don't. If we had a different object that was generating a force with the child, if we were moving into an electromagnetic force where you can still get a large force between two objects of small and similar mass, then you've got a different issue. Or if these were two planets that were gravitationally interacting, then we'd want to look at things a little bit differently and not just jump straight into this simplified approach for conservation of energy. But in this case, it's fine. So hopefully that's made things a little bit clearer. There's quite a lot of depth in this question outside of the, on the face of it, a pretty simple question to solve.